Well, welcome back, everyone. Today, in episode 19, we're going to start talking about branch control in the Apollo guidance computer. So I'm going to go to the kind of the diagram. This is one of the diagrams that we looked at actually in the very first episode, which is a different kind of logical breakdown of the guidance computer. We've spent a lot of time going through things like the addressable central registers. We've talked about the memory address register, the G register, kind of the special gating, those kind of left and right shift editing control. Um, and now we're going to start talking a little bit about kind of instruction decoding. Now, before we get into the SQ register, which is the actual kind of sequence register and kind of how we actually generate those control pulses we've been talking about, I'm going to spend a little bit of time talking about branch control and kind of how that works in the AGC. So let's go back and look at, let's move this out to the side, kind of how the AGC kind of goes through and create sub-instructions from the control pulses. So as we've talked about in some previous episodes, the guidance computer will basically sequence or step through these kind of 12 actions as it goes through the process of executing a sub-instruction. So we've got these different sub-instructions. In this case, we've got, AUG 0, DIM 0, MSU 0, read, write, so on and so forth. And at each kind of action will generate a sequence of a series of control pulses. So for example, here at time 02, if we're executing the AUG 0 sub-instruction, we will trigger an RSC and a WG control pulse at the same time. So we talked about that and kind of how that works, and then how we kind of push data onto the right lines or read data from the right lines. Um, but there's a bunch of other instructions that allow us to start doing branching, and that's kind of in any computer what will truly make it Turing complete is that we can do branching based on various conditions that the computer encounters. So the way that the AGC does that is through a combination of basically test control pulses. So you can see, for example, here we have this TSGN, or sorry, not TSGN, the TMZ command here, or pulse. Um, and then what it does is we can see here, as we get into time 6, we've got this kind of triangle 1, triangle 2, triangle 3. And this is where we basically will branch. So we've got option 1 is we'll issue a MONX control pulse. Option 2, issue a PONX. Option 3, no control pulse at all. And then if we go all the way to here, it'll actually show us, okay, what conditions will trigger the various 1, 2, or 3. So basically, triangle 1 is if BR0. So this is basically, if you look at it, there's two branch register or two branch flags, if you will, or a register that's 2 bits. So it'll basically be, if it's 2 bits, that gives us the options of basically 0, 1, 2, and 3. That's basically the 4 different options that we can have within those 2 bits. So basically, say if that branch register or those 2 flip-flops contain a 0, then basically it's because we've executed one of these tests. We will then execute this. If the branch register contains a 2, we will do this. If branch contains a 1 or a 3, we won't do anything. And then we can also see, for example, here we've got options 1 or 2. If branch contains either a 0 or 1, and you can see at time 7. So if I actually look at time 7, that's actually when it's running that particular test. And then based on that test, again, we execute a 1, or we execute option 1, which is do nothing, or option 2, which is we'll read data into the A register, we'll write data into the Y register, and we'll issue a MONX control pulse. So that's kind of how the AGC does that by issuing these sort of test command pulses. So let's look at what are those control pulses that we have within the AGC in order to perform these tests. And so there are 7 in total, and we've got those two 1-bit flags, BR1 and BR2. And so, for example, we've got this one here, TL15, which basically copies the content of whatever bit 15 is of register L into flip-flop BR1. We've got TMZ, which is basically a test for -0. So test all the contents of the, in this case, WH, so this is the right line. So if the right lines contain a -0, i.e. bits 16 through 1, so basically all your bits are 1, because this is a ones complement machine, then we'll set BR2 to 1, otherwise BR2 is set to 0. Then we have this other one here, TOG, which is test for overflow. And it basically has 2 options. If it's a positive overflow, we will set BR1 and BR2 to 0, 1, or 1, 0 if it's a negative overflow. And basically that will look at the contents of the right lines bits 15 and 16 to determine whether or not we have um, a negative overflow or positive overflow. So in the case of a positive overflow, bit 16 will be 0 and bit 15 will be a 1. In the case of a negative overflow, bit 16 will be 1 and bit 15 will be 0. So those are the 2 conditions. Essentially, we're almost writing the contents of 16 and 15 into the BR1 and BR2. We have this TPZG, which is test the contents of G for +0. So basically, if bit 16 through 1, so all of them are 0, then we set flip-flop BR to 1. Otherwise, the contents of BR2 is not changed, so we won't change it if we don't have to. We have this TSGN, which is test the content of right line 16 for sign. If it's a 0, flip-flop BR1 is set to 0. If it's a 1, BR1 is set to flip-flop BR1 is set to a 1, and we don't touch the contents of BR2. TSGN is basically exactly the same thing, except we set BR2 instead of BR1. So it's a slightly different option. And then we have TSGU, which tests the contents of gate U16. Basically, we're checking to see the contents of our adder if we have a positive or negative number, and based on that, we will set BR1 to 1. So it's a little bit different. Like if you compare this to say like the 6502 processor, 6502 has several kind of status flags that the CPU uses for branching. So based on basically whatever the last instruction or the last operation that was done by the ALU, the 6502 will set different flags. If the number is negative, if the number is 0, if we had an overflow, if we had a carry in the last operation, and then there's a number of instructions that will basically check the contents of those flags. And if, for example, if it's a positive, then if you check the negative flag, then do a certain action. If it's a positive number, do a different action. If we had an overflow, do one action versus a different action. So there's very specific flags that indicate a specific condition, whereas we kind of do these tests, and then based on these tests will then set those flags, and then based on the next instruction, we will determine how basically what option to take as we continue to run the program. So this means that as we get a little bit further and start doing the actual instruction decode, we not only will need to look at things like the contents of our sequence register, so the instruction itself, but we'll also have to look at the contents of our branch flags to determine basically what control pulses to generate. So the AGC itself does this through sort of diode logic, this kind of cross-point logic that's mentioned several times in the documentation of basically how it generates these the various control pulses as it goes through the execution of its instructions. So how does this look when we actually start getting into the circuitry itself? And it does start getting a little bit complex. There's a fair bit of logic that I had to kind of work through in order to kind of build, based on the appropriate control pulses that we get in, how do we actually generate the appropriate either set, or basically the right input for our D registers here. So here's our BR1 D latch. Oops, I'll switch right back. So we've got sort of our BR1 deregister here, and then our BR2 here. And then we have a variety of inputs for various control pulses. And then based on the control pulse, we have certain things we'll evaluate again. So for example, we have the TL15 control pulse, which inserts the contents of L15 into BR1. Here we have the TPZG, and this is basically a control signal that I've generated myself called G is 0, just because of the logic. It didn't make sense to basically pass the entirety of the contents of the G register, so all 16 bits, to this particular board. I basically will do the test on that board, basically on the G register board itself, basically using a series of AND gates to determine if G is 0, and then I'll actually put that G is 0 status on the back plane so that I can pick it up here and do the comparisons. The others look at L15 contents, the contents of the adder bit 16, and then all of the others look at various write lines. So I've got the write lines are available on the back plane. This is some additional logic here that we'll talk about in a different episode as to basically what I call bus control. There's a variety of other instructions that load certain constants onto the write lines. So we'll come back and talk about that later. But the logic here is of basically taking an AND. This is for our TMZ to see if it's -0, our test for -0, which is basically if all of these are ones, we'll do some logic on that to determine that yes, we meet that condition, and then based on that and a bunch of other logic, determine when do we set the appropriate bits or clear the appropriate bits. So we'll just pop over into the simulator and kind of show how this kind of all comes together. And again, it's a lot of logic that kind of pulls all this together. But most of it's actually like if you start working through it, it's a case of we have a control pulse, and then we have a condition that we have to either test against. So we need some, like in this case, is G0. So we have basically if the control pulse, and of course, because we have negative logic, so we invert that. If G is 0 and the control pulse has been asserted, we basically AND that, and that generates our, basically we need to set in this case, BR2, and then we'll OR it with a bunch of the other conditions that will set BR2. So, we have this condition that'll set BR2. There's several other conditions. We kind of OR them together. Because in some scenarios we want to maintain or basically take into account the contents of the branch register, it does kind of loop back around a little bit just to make sure that we don't reset the values in certain circumstances. And then you can see up here, we actually have a little bit of logic around our write timer. So this is to generate our clock pulse to either set, because sometimes we want to set these, and sometimes we don't. So for example, you may have, and that's kind of going back to this scenario here, is that we may do a test earlier on in our cycle. So we do this TSGN test on time 7, but we don't actually do the branching until time 10. So basically, even though the clock is pulsing as we go through each of these sequences, we don't want to, because we're not doing any other tests here, we don't want to lose the contents of those branch registers as we kind of progress through the logic, or sorry, as we progress through the various sequences in or various actions and the control pulses that are generated. So that's why we have some of that logic here to determine, well, when do we want to actually pulse the clock either for BR1 or BR2 based on, A, do we have any of those test control pulses asserted? And then we also have a little bit of other logic because there are some cases where we just want to leave the other register alone. So, for example, if you look at the TSGN and TSGN2, part of the this instruction on that is that we have this without changing the TSGN. We do not want to change the contents of BR2. So we'll set BR1 based on the sign of whatever data is on our write lines, but we will leave BR2 untouched. For TSGN2, we do the opposite. We don't want to touch BR1. So again, we'll use some of that logic in order to determine when, for example, you can see these little two AND gates here, will determine, based on TSGN2, for example, being asserted, it says that we want to leave the contents of BR1 unchanged. So we basically have this little AND here so that even though if we pulse the clock, we're not actually going to pulse BR1 in this particular circumstance. So we'll just leave whatever data is in that particular D latch. So with all that kind of builds our kind of logic in order to kind of set these two bits. One thing that I'm still haven't quite figured out is, so you can have a scenario, and I'll just go back to the PowerPoint. For example, we've got TL15 and TSGU is another example. So this is where, well, we set the contents of BR1 essentially based on the contents of whatever is in U16, so the sign. So if it's a 0, we set BR1 to 0. If it's a 1, we set BR1 to 1. Now, the one question is, I'm not quite sure if the intent is that the AGC will just maintain the contents of BR2 to whatever it is. It doesn't mention it. Like, for example, here it says without changing the contents of BR2, but it doesn't say it will just clear it out. So right now I'm assuming, because it doesn't have this, without the changing of the contents of flip-flop BR1 or BR2, that for a TSGU, it will basically clear the contents, versus, and TL15 will also clear the contents of BR2. Because in the other ones, it actually will explicitly say the contents are not changed. So if we get into the bill of materials, in order to build this out, I don't have a picture of the board. I'm actually starting to, actually, these videos are starting to get quite a bit ahead of the actual hardware I'm starting to build. So I may need to take a week or two and start catching up with some of my soldering and wiring to start actually building some of these. But we've got the 74LS74, which is our dual D type flip-flop that we'll use to actually be our BR1 and BR2. We've got two LS704 hex inverters, three LS08 quad 2-input AND gates. We've got two 74LS27 tri 3-input NOR gates, three 74LS30s which are 8-input NAND gates, and so we're basically using this to either generate our clock to only clock these registers when one of our test pulses is asserted, and then we're also using this to check the contents of the write lines for certain conditions. Then we also have one 74LS32. This is a quad 2-input OR gate. Our buffers for clock and reset. And in this case, we just have the two LEDs that we're using to basically show the contents of the BR register, or the two bits, BR1 and BR2. And then we've got just one bus resistor and then ceramic capacitor for those bypass for those chips. And then, of course, our bus connector, or backplane connector. This card, I'm probably, the way that I'm building it out is I'm actually also going to use this to display the contents of the write lines itself. So on most of our boards, we've got LEDs that will show whatever the contents of the register are. So I've got some extra real estate here that I'll use this card to actually show the contents of the write lines itself. So I can see what data is being pushed onto the write lines, and making sure that the data is flowing correctly as we start to build up the computer. As always appreciate everyone's feedback. Please subscribe. Like I try to get these out once a week. I may be, like I said, just to catch up on actually building some of the hardware. I may start moving to more of a 2-week cadence, so I can catch up a little bit there. But with this, the next episode, probably going to talk a little bit about some of that bus logic and how we can push certain constants onto the bus in order for the computer to operate. And then we'll start getting into the sequence register and the instruction decode. And that starts getting a bit complicated because there's not only do we need to decode the basically the contents of the sequence basically register in order to generate instructions, but we need to combine that with branch. And there's a few other flags that are kind of part of the process that are used in order for us to generate the appropriate instruction, things like the extend bit and a few others. So it'll probably be a couple episodes for us to kind of work through instruction sequencing and the sequence register. It is probably, I'd say, the single most complex piece because there's timing, there's clocking, there's certain control pulses that actually reset that action timer. So it's not always 1, 2, 3, 4, 5, and up to 12. Sometimes it goes back, and sometimes it sets it to certain values in order to get the instructions to execute as expected. But that'll be our next episode. We'll start getting into that. And like I said, as always, if you see anything that I've made a mistake on, please feel free to comment. Always looking to learn and improve as I start building the replica out. Thanks again, and we'll see you probably 2 weeks. Like I said, I'm going to spend next weekend building a bit more so I can start catching up. But we'll see you then. Thank you.